Thank you everybody for attending my talk today. Thank you, John, for organizing this marvelous event. It's indeed absolutely outstanding. And I would like to talk about something that is extremely simple, how to compute geometric progressions, a task that is certainly easy for most of you, but we will see something that, in fact, the computational complexity of this simple, extremely simple problem is, to put it mildly, not too well understood, and we will see that it, despite the fact that, as we shall see today, it has enormous amount of practical applications, including probably the most high-profile application, Google page ranking algorithm. We will show something surprising later, that we can convert, in fact, computation of every single polynomial into evaluation of several geometric progressions. And at the end of the talk, I'll compare a few specific computational experiments with polynomials for floating point, single, double precision, and posits. And as we might anticipate, in any case, posits are defeating the computation by quite, in terms of precision, by a large margin. So let's move forward. So here, this is the problem. Compute this: 1 plus x squared plus x cubed, and so on. Up to, usually, we fix to degree x to the minus n minus 1. So, of course, we can compute it as 1 minus x to the power of n over 1 minus x. But what if we don't want to do the inversion? I mean, there are indeed many practical cases in which the inversion is rather costly. For example, for those of you who might be familiar with encryption, inversion of finite fields is a very time-consuming an operation, so it's not quite a good thing to compute this if we can afford to do the computation only by making use of multiplications and additions. A few applications, matrix inversion, can be easily converted into such a computational series, assuming that the spectral radius of the matrix A is less than 1. If it is not less than 1, we can do some preconditioning and convert the problem into the same summation. How to do the summation, and of course we cut the summation up to a particular point in a most efficient way, is not quite well-known a problem, despite the fact that it has many applications in digital filtering, in graph theory. I'll specify application in graph theory today. Computational tomography, radon transform can be converted into the same summation, optical computing, and as I pointed out, in the Google page ranking algorithm as well. So here is the standard thing that is usually recommended to do. This is a formula suggested by Euler, and actually it simply says that every single number, integer, has a unique representation in binary number system. If that's the consequence, convert the summation into a product, the product is given. Usually we cut the summation up to a particular point, and if we cut the number of terms to be a perfect power of 2, we have this particular statement, and this specific approach is utilized in the Gauss-Smith division algorithm. People who implement floating point division algorithm make a good use of this formula. Usually when we implement A over B in floating point, we invert 1 over B, then multiply by A to get the result. And this particular factorization is in fact used in the algorithm itself. So here is the way. So we can treat, let's say, here is the polynomial, decomposition and multiples. And if you, let's say, have to compute 1 plus x to the 15, and if you decompose it like that, it takes 6 multiplication. You can see 1, 2, 3 to compute the powers of x, and 1, 2, 3 in here. If we need to go further to 31, it's really nice and convenient, seemingly, that we have to just add 1 additional term, and we increase the number of multiplication only by 2, and so on. So, very well. Can we do better? It seems surprisingly that the answer is yes, but here, oops, no, I think, okay, here is one example. In the previous example, when we consider the polynomial degree 63, we have an algorithm with 10 multiplications, and if you just very carefully follow this thing, you can see that in fact we have 9 in here multiplications, which is quite surprising. But of course, the whole point is, how do we design such a thing? For example, if you can remember the Strassen's multiplication algorithm, it looks like a complete mystery. Absolutely nasty thing is that Strassen didn't publish the way he described the algorithm. You just see, you can multiply 2 matrices 2 by 2 with 7 multiplication. How? Well, the simplest answer is could have been provided by stress, and I'm so smart I can see these things. But what about finding these things in a more logical way? I'll try to explain how to find decompositions like that. What are the savings that we can get? Are they massive? Are they marginal? Etc. And let's see. So, evaluating the standard polynomial requires 2k minus 2 multiplication if we're using Euler's formula, assuming that we are cutting the number of terms to be a perfect power of 2. So if you have to evaluate such a thing and the precision criteria is not met, so for example x of course must be less than 1, otherwise the series diverge, we degree we double the number of terms and it costs only 2 multiplications. But you will see today that there are some surprising things. For example, in evaluating the following polynomial 1 plus x to the 127, the Euler's formula, as we saw, requires 12 multiplication. But if we go to 129, it's not a mistake, it's indeed 2 more. We can do it in a very tricky way with only 10. So if we have to evaluate such a sum, sometimes we can get even higher precision and less number of operations. For some reasons, I hope they will become clear after today's talk. So that's okay. Okay, so we will see how to generalize Euler decomposition, and we will see several non-trivial consequences of these findings in today's talk. We will see particularly applications to matrix polynomials. The evaluation of a matrix polynomial is fundamentally different a task in comparison to the evaluation of a classical polynomial. First of all, in here, if you want to use matrix inversion, so that would be I minus a to the power of n times I minus a inverted, but the matrix I minus a might not be invertible. So we are looking for algorithm evaluating polynomial g without making use of any matrix inversion, and we will see how we can do that today in the most efficient way. So let's consider firstly just the polynomial thing. If we consider the polynomial of degree n minus 1 and n happen to be a composite number k times j, then we can decompose the polynomial into 2 polynomials of smaller degree. And basically, in the case of if n is a perfect power of 2, we are using k2, and we are obtaining the classical Euler decomposition in this way if we just repeat recursively the formula. So the number of terms is becoming 2 times log n in base 2, and this minus 2 is just a consequence of the very detailed analysis at the end of the algorithm. So what about if we use base 3 decomposition? And by the way, this formula is always recommended to be used in practice if we have to compute such a things. And in today's talk, we will see that this is not just suboptimal, this is the worst, the formula with the highest computational complexity. Any base different from 2 would perform at least as good. So in the case of ternary base decomposition, we have the following formula, and number of multiplication turns out to be 3 times log n in base 3, and if we convert the function x times log n in base x, we can see that the optimal value is e, which is pretty a common thing. Frequently people say base e would be the optimal base if we consider number system with any kind of basis, but in this case, because 3 is closer than e, we're getting a little bit better performance. 5%, the difference between 2 and 1.9, but still something, and not noticed up to now. Meaning that if we have to cut this summation to a particular point, it seems a little wiser to cut to the closest power of 3 as opposed to the closest power of 2. We'll save something. Well, it's not a big thing, so how about try the next base, base 5. So if we cut to the power, if we use the same idea, we can see a formula, and it seems like, but it's not exactly true, that the number of multiplication is 5 times log n in base 5. And when we can convert everything to, there is a typo here, this is 2, okay? If we convert that to base 2, we get constant 2.15, slightly more than 2, so base 5 seems to be not exactly useful, but that's not exactly the case, because here is what the algorithm should look like. If we use base 5, we decompose the product in this particular way, but the polynomial here, the polynomial here uses x squared x to the power of 3x to the power of 4. So how many multiplications we need? 1, 2, 3, 4, and then we compute x to the power of 5 and apply the same trick in here. It seems 5 times log n in base 5, but the trick is that this particular polynomial can be factorized in the following way, using 1 2 multiplication. This is pre-computed, and then from this polynomial we can reconstruct x to the power of 5 by using only one single multiplication. Small trick, but with serious consequences, because in here we can reduce the number of multiplication to 4 times log n in base 5, and the constant decreases to 1.72, which is quite an improvement in comparison to the binary, to the Euler's formula, almost 15%, and we will see that we can do even better than that. Okay, so that's for, in terms of the base 5 decomposition. For the base 7 we can use similar tricks. You can see that now the constant here is becoming a little worse than base 5, but better than base 2 and base 3. So let's try to figure out what we can do in the general case. In the general case, we may need to compute the same polynomial for not just designed by us a degree, but for any degree, let's say 100. In this case, it's not a power of 3, 5, or 7, just 100. Well, just if we're using the following decomposition of the polynomial, so if the number of terms is even, like in here, we're decomposing the polynomial to the polynomial of degree half by making use of this formula. Otherwise, if it is odd, we're using the same thing. You can see that the number of multiplications, so the cost to convert the problem from size alpha to size alpha over 2 is 2 multiplications, one for this and one to multiply here. The same in here, so that's why we anticipate that the number would be 2 times log 2 in base alpha. To log alpha in base 2, and there is an additional term which is a little too technical to evaluate, but you can take it for granted from me that this is indeed the case. So in the general case, if we use any base, we are obtaining the following formula, and it turns out that when we consider different bases that we can use to evaluate this, base 2, which is usually the recommended choice, or base 4, base 8, base 16, they're in fact the worst bases. Base 5 seems to be terribly good. Base 7 is nice. Base 11 is good. Base 26 is not on the table, but we'll see that actually we can improve even this graph, showing that base 26 can do a little better than base 5. And we will see what would be the... Actually, there is no such thing as optimal base in this case, but how can we obtain a sequence of bases that improve upon each other? Okay. So that's the thing. So how can we implement the same thing over matrices? Over matrices, we apply, of course, the same formula, which is like that. So a problem of size n is converted into problem of size n over 2 in this two possible ways. But what about if we have, let's say, if we convert the problem from size n to size n over 3? Well, the same decomposition is possible, and if the formulas are correct, and if you see what is the cost of converting problem of size n to problem of size n over 3, well, given the matrix A, it takes 1, 2, 3 multiplications. Here is 1, 2, 3 as well, but here is unfortunately 4, 1, 2, 3, and 4. So we can see that in fact base 3 has a little bit strange structure, so that's annoying, but that's fine. So when we convert problem of size n to problem of size n over 3, if n is exactly divisible by 3, we need 3 multiplication. If n is 1 modulo 3, we need 3, but otherwise we need 4 in the last case. Whereas in the case of binary algorithm, we have a nice, easy to analyze structure complexity. It takes always 2 multiplication to convert problem of size n to problem of size n over 2. So we are very happy if our n is having only zeros and ones in its ternary representation, because we are always taking the path with only 3 multiplication. But sometimes we may need to take and to use 4. So clearly we have 2 different algorithms, and can we take the best of both worlds and combine them and to obtain a new algorithm which will work even better than these 2? And what would be the consequences? What would be the computational complexity of such a thing? We'll see in a minute. So the average complexity of the ternary algorithm is the complexity varies between one constant. In the best case, it's 1.88. We are always going here. In the worst case, it's 2.52. If every step of the way we need 4 multiplication. On average, it's 10 over 3 multiplication times log n in base 3, which is 2.1, not 2 log n in base 2 multiplication, so it's slightly worse. So the idea to mix the 2 bases, if we mix base 2 and base 3, we got to work modulo 6, and now the formula is becoming the following one. And how do we analyze the complexity of such a thing? Remember, what we said in here is that we are happy if n modulo 3 is 0 or 1, otherwise, and we take this particular path. Otherwise, instead of taking this path, we apply this formula. So it seems like a little bit strange number system. We divide by 3, and if we accept this, if we get a residue 0 or 1, we accept. If we get a residue 2, we say sorry, we divide by 2. So we have a number system which is clearly having an average base between 2 and 3. We more often divide by 3, and sometimes we divide by 2, and what would be the average base, what would be the actual complexity in this case, remains to be analyzed. And the analysis can be done by using standard either finite state machine analysis or Markov chain analysis, when we have different residues modulo 6, 0, 1, 2, 3, 4, and 5, and consider the transition probabilities. And when we solve the probability model, we come to the conclusion that base 3 is occurring 60% of the time, base 2 is occurring 40% of the time on average, and the average base in this case is 3 to the power of 0.6 times 2 to the power of 0.4, which is quintic root of 108, which is 2.55, and the complexity is reduced to 1.9245. So the constant is slightly reduced, but it's a good achievement, having in mind that the formula, Euler's formula, was considered as the best for, well, basically for centuries. Okay, so here is the same thing for the matrix decomposition. We apply exactly the same formula, modulo 6. Basically, if the number is divisible by 3, we apply this formula. If it is 1 modulo 3, we apply the ternary algorithm, and if it is 2 modulo 6, we apply one of the formulas for the binary base, and otherwise the second formula in the base 2 decomposition. So once we know that mixing the bases gives us good result, why don't we try any kind of mixing basis? Of course, we can mix more bases, we can mix 3, 4, and so on, and we can select exactly good bases, and actually it even matters under what condition and how do we order the bases, but it's a little too longer to explain why. Still, the constant, as you can see, that the constant can be reduced to 1.79, and probably can be reduced even a little bit further. The most interesting decomposition perhaps is base 2 and 5, because if you consider double base with bases 2 and 5, you can very easily mimic the decimal number system. Base 2 serves as the connection between these two bases, and this is a very interesting topic for research. Many of these things can be found in a book that I will show you at the end of the talk. Okay. So let's move forward. Now we can see in here that actually base 26 can be implemented, can work a little bit better than base 5. So here is the decomposition. If we have to compute exactly the polynomial of degree 24, you decompose it in the following way. So it takes, in here you evaluate this polynomial with only 2 multiplication, not 3, like in, because there it can be nicely factorized. Then once it is done, you compute x to the 5 with 1 additional multiplication. Then you evaluate this with extra 2, and there is one final, so it's only 6. And you can do the same thing for if we have 25 terms. And now with base 26, you can get this particular constant reduced to 1.702, which is almost 15% better than the Euler. And we can actually, once we know how to convert from one base to a better base, we can see that base 667 works a little bit technically better than 26, and we're getting a very curious sequence in here. This is a sequence which is defined like that. The first term is a 1. Every new one is the square of the previous one plus 1. And every new, and this one, so basically from 1 we're getting 2, the next one is 5, then 26, 6, 7, 7, and so on. And the limit of this sequence, it's a theorem by Alfred Tahoe and Niels Sloan, which is not exactly easy to prove, is given by the following formula, and the constant C can be analytically computed. So we can see that we cannot, if we apply the entire analysis, the constant based on combination of these methods cannot be lower than 1.701. Whether or not it can be done we can go lower than 1.7 remains to be seen, probably, but we need some radically different approaches to achieve such a thing. So here is a series of few examples how to compute this polynomial of degree 255 if we just decompose the 255 in base 5, which is given here, and decompose the polynomial in this clever way. It takes only 12 multiplication as opposed to 14. It may not seem like a big reduction, but still it is. It is good, and it can be used, for example, if we have to implement a Goldsmith division algorithm. If we decompose the 1 over b, use the decomposition like that, we can save multiplications, and that's certainly an important thing. Here is the example how to. That's a very detailed explanation how to compute these things if we have to. And here is, for example, if we have to evaluate the same sum, and we conclude that the first 120 terms will suffice, will satisfy the precision requirement. What is the optimal way to compute the series? Well, you can compute this with. We know that Euler's formula requires 12. We can do some tricks to get 11, but in fact, if for 130, because it's a product of two really nice primes, 5 and 26, we can get only 10. So the question is always in here how to find some really interesting properties of the number of terms, which is 130 here, like 526, and find a good formula for this thing. Okay, so let's see some interesting possible practical application. One massive thing, of course, is the solving linear system, and a very nice way, which is quite close in spirit to the Jacobi-Zirel method, is this one. When we have to compute a times x, we represent the matrix a as I minus ax, and the inversion of a to the minus 1 is converted into the following series in here, and of course we're going to cut it at a particular point. We need one particular condition to satisfy that the spectral radius of I minus a should be less than 1. If this is not the case, we have to do a preconditioning, and I'll see what will be. I'll explain what will be the cost of this preconditioning later when I showcase specific timing results. So. We have a good algorithm for preconditioning, but we are quite sure that we can do considerably better in here. So we compared our findings with Intel MKL library solver, because this is a really well-designed code which is massively used in many industrial applications, especially in the city of Calgary. There are many geophysical companies doing research in the field of massive geophysical data analysis, and for them, MKL is the de facto choice to solve all kind of matrix problems. And we experimented with dense, non-symmetric real and complex matrices. There is a big difference between real and complex matrices in the favor of the approach I'm going to explain, and we will see why this is the case now. So if we just cut the number of terms to 30 in the summation that I outlined to 32 or to 60, to 31 in fact, and to 63, we have two different algorithms, and we compare with the standard LU decomposition. And in this case, we are seeing that the complexity grows in a very much nicer way in our case, as opposed to the classical approach aimed at solving systems of linear equations. So let's see some other data. So more accurately, if we cut the number of terms to 63 up to problem of size 300, we start to defeat the LU decomposition methods. If we cut the number of terms to 31, and you'll see that the precision is not that bad even in this particular case later when we see the tables, it is like 60 or 70. If we take the cost of decomposition, we start to defeat the LU decomposition methods when the size of the problem is getting like close to 1,000. So here is the specific set of data for in comparison with the LU decomposition method, you can see that the precision measured in the classical error norm when you divide the second, when you take into account the second largest eigenvalue of the matrix is satisfying these restrictions. At the size 300, we already beat this with completely similar error metrics, and when we go to very large, well, not very large, but reasonably large size, like 4,000, the ratio is massively in our favor, and you can see that in terms of precision it's still within order of 10 to the minus 15, and if we accept a shorter series you can get lower but possibly quite acceptable on error metrics, and the price is, as you can expect, twice as low. So clearly this is showing a very, very good performance characteristic. In the case, just 1 minute for the complex case. In the case of complex computation, we win even more. Why? Because LU decomposition uses divisions of floating point numbers, and division is a very slow operation. One division, some of you may know that complex division requires 6 elementary operations, and there is no way to get it with 5. So, whereas our algorithm uses only addition and multiplications over real numbers, which is quite a good thing, and that's why we are having a gain with a similar matrix error performance. We are defeating quite convincingly the LU decomposition methods by a large margin. We compared with Koleski methods and etc. and in other cases, and still we're doing better than the approaches classically used. Now, for the next minutes of the talk, I'll show you how we can convert matrix polynomial into geometric progressions, and then we will see the results with these for the experiments with posits, signal precision, and double precision polynomial evaluation. One problem which is of huge importance in quantum mechanics, for example, is computation of matrix exponential. Compute something that is pretty similar to what I explained, except that we have this. Okay, so how do we compute this thing is a problem which has been investigated for quite some time, and nevertheless there are still way too many open open tasks to be investigated. In 1979, there is a marvelously good paper called 19 Dubious Ways to Compute Matrix Exponential by Van Loon, and in this paper, the fact that you have 19 dubious ways, 19 certainly means this is a good thing to investigate. Dubious, well, there is something to investigate in here. And there is a lot to investigate in here, how to compute such a thing, because frequently we may need to compute the series to a very high power, a to the power of n over n factorial. A to the power of n might become so large that you may have already an overflow. So how do we compute this problem? So we was, in last year's ARIT conference, I showed, and I'll very briefly explain how we can convert this particular problem into several problems of the spirit that I explained without the use of this factorial term in here. And how we can do that? Well, first of all, we would like to compute the exponentiation up to when we take the matrix a to the power of n minus 1. And first of all, let's consider the following system of n minus 1 nonlinear equations. The sum of alpha, the constant alpha 1, alpha 2, all the way to alpha n minus 1 should be determined. So we compute this particular constants, and then we convert the evaluation of the original polynomial into the summation of our polynomial g, which contains only which is just a geometric progression, and we multiply the matrix 8 times pre-computed constants. So, for example, here is how do we compute the polynomial of degree 4 in here with in this way. So what we need, solve the system, which this is a toy example, and of course it can be solved for much larger problem sizes. Like that, we obtain the solution, and this is in this particular case the solution is complex. But one thing, there are methods to avoid complex arithmetic, and something that is more important perhaps in quantum mechanics, always the matrix A is complex, so it's not a big problem that we have to evaluate complex matrices in here. So we decompose in the familiar way and we save computational time. When we implement this particular algorithm and compare with the built-in MATLAB implementation of the function MATXPIN in MATLAB, we're 37% faster, which is quite a nice thing. They use polynomial of degree 13 to approximate the series, and that's the numbers are way too big to show here, but I can show the actual coefficient, etc., if you're interested. And now let's see the computing the polynomials with posits result from our MATLAB experiment. My PhD student Diego Coelho, and Dr. John Gustafson knows him very well. We decided to create a small MATLAB library that implements the posit arithmetic, and we just calculated several polynomials with standard fixed point floating point arithmetic and with overposits, and we compared the things. So we compared with three types of polynomial. Neumann polynomial, this is just the same polynomials I considered. Sometimes they're called Neumann polynomials, 1 plus x to the n minus 1. Bernstein polynomials, they're extremely useful in digital filtering. They have the following form. They are almost flat at point 0 and 1. And they're quite useful, particularly in digital filtering design. And Wilkinson polynomials, they're quite notorious for their numerical instabilities. And you can find the actual mathematical description of these polynomials everywhere in the numerical books. And here is the result. First case, in the case of Neumann polynomials, we use for posits and for floating point, we use two different specific data representation with 32 bits and with 3 regime bits, with 64 with 4 regime bits, and the precision for the degrees of polynomials of small degree 3, 4, 5, 6, and 7. In any case, the posit arithmetic offers better precision in comparison to the floating point for single precision and for double precision. In the case of Neumann polynomial, for example, if we take this in here, it's 1.67 times 10 to the minus 6.32. In here, it is 2.20 times 10 to the minus 6.32. So that, we decided to calculate these things, and we saw that in any case, posit arithmetic offers better precision. In the case of Bernstein polynomial, we are seeing a similar picture, and in the case of Wilkinson polynomials as well. So to conclude my talk, I think I'm doing right on time. The fastest, we are offering for now the fastest algorithm for a variation sum of consecutive powers. Are they the fastest algorithm fundamentally? I don't think so. Maybe it is possible to reduce the constant from 1.7 below. For sure, you cannot get below 1. But having in mind that it's a really important practical problem, it seems like a very good task for if you are interested in just this particular problem as a theoretical computer science problem. There are very powerful applications in the algebra algorithms, and I think we saw some of these things today. We are showing a radically new approach for polynomial evaluation over scalar matrices. Why it is different? I just demonstrated in here how to solve the system in the case of matrix polynomial, but for any polynomial, whatever you want, just change this. Change the right-hand side with any coefficient right here, solve the system, and you will have an int, and that's it. That's fine. All you need is to change the coefficient of your polynomial, put them in here, you obtain the constants here, solve the system, and evaluate the polynomial at this particular point. But that's a rather powerful approach, because as long as you have a quick inverter, you can do everything, and they're completely independent each other. So that's a very interesting finding. So far, we tested this only for the matrix exponential, but it works for any polynomial imaginable. So that's what I can, and what else I said. Okay, yeah, the comparison is the last thing we have done. I'll ask Diego to put our MATLAB library into the POSIT hub, and we'll do that so we can see how we implement it. I'm pretty sure that the implementation is suboptimal, but at least it's working, it's tested, so we can, so people who would like to use POSIT with MATLAB, now they have the tool. Okay, thank you so much.
Thanks, Vassil. So we have a few minutes for questions. John?
If you
Roll back a couple slides. I don't understand your error comparison between positives.
Yeah.
You got 10 to a fraction.
Yeah.
Fraction.
Oh, that's one. Yeah.
Get hold of the
Let's say
What do
this
those
one,
things
for
mean?
example. Well, that's.
What
yeah.
are these entries?
Yeah, I will explain. So basically, for example, consider the floating point case in this case of single precision. So degree 5, this is x minus 1.
We need your microphone.
Oh, yeah, okay.
Here you go.
So it's x minus 1 times x minus 2 times x minus 3 times x minus 5. This is the polynomial degree 5. We collected we decided to compute the polynomial exactly at point that are close to the roots of the polynomial, because at this particular point the behavior of the algorithm is rather poor, and we noted that basically 10 to the minus 4.82, this is how many bits, like 10 to the how many bits? Yes, how many bits of precision is that? 10 to the we calculate everything in binary. So this is the case, like close to. Oh, this is minus in here, of course. So this is 15 times 3, around 46 bits of precision. Okay. So in here we have the same thing, but the constant is smaller, and we're saving basically like 1 bit of precision. In here, already when we go to degree 7, we are saving the ratio between these two things is telling us how many bits better we are having, and this is close to 2. I don't know why we decided. Well, basically, when I asked Diego to run the code for the positor, he gave me this table, and I adapted my calculations to compute they're making sure that this exponent is matching to this. So we can easily see what we save.
Okay.
So that's weird, but I got this basically last week, and I decided, okay, I'll calculate my errors in this way just to make sure that everything is easily comparable.
So if you lose 14 decimals from double precision, you don't have anything left, right? Hardly anything left.
Yeah. Well, yeah.
1 decimal, correct?
Yeah, that's one. That's in here.
So how many decimals right did I get?
You're getting decimals. You're getting 10 to the minus 14, and you have to get 10 to the minus 17 if you want. So you're losing basically 2 and something. Okay, 2 decimal places. In here as well, but lower precision. But we're reducing this constant. Yeah, yeah. But, the higher the degree of the polynomial, the more you save. This is because we are having very low degree polynomial.
Any other questions? I have a question.
Yeah.
So in choosing the base, you're actually trying to minimize the number of multiplications,
Yeah.
right? What are the implications of that on accuracy? Are there some bases that reduce the number of multiplications but might not give you such accurate results?
In this case, actually, it's you win in both directions. And the question is actually, what is the criteria? In our case, we are trying to minimize the number of multiplications. But in some cases, like in encryption, for example, the problem is a little bit different. In there, you have 1 plus 2 squared plus 2 to the power of, let's say, 162. This statement, you minimize it, you decompose it in such a way as to minimize the number of plus signs, which is ridiculous, but it's exactly what leads to very efficient things. In some other cases, you may need to minimize the number of terms for different criteria, but in terms of precision, the less the number of multiplication, the more you save either, in terms of accuracy.
All right, thanks. Okay, well, if there are no other questions, then let's thank Vassil one more time. Thank you.